Welcome to a new video. In this video we will discuss an example of an inverse z-transform. This will be example number 1. The z-transform and an inverse z-transform are very useful in discrete time control systems and DSP applications. We will see how we can do that step by step in this example with the calculations. And also verify this in MATLAB command so you can see that the calculations are indeed correct. Okay, let's see our example. We would like to determine the inverse z-transform of this function, which is given by f of z, which is a parameter in this case. It's given by 0.4 z over z minus 0.5 times z minus 0.6. So we have two poles and 1, 0 for this function. Okay, so how do we determine that? Let's see first the calculations. First, we start with dividing our function by z. So we have this function, you divide the complete function by z, which means you take this one, you divide by z, so you put in the denominator a z here. Now, since we have already a z in the numerator, they will cancel each other out. So we have here this expression. Now we will use this expression in the next step using the partial fraction expansion. Now, that goes like so. We expand this in two parts, so we divide it in two fractions, a summation of those two. We put the z minus 0.5 here and a z minus 0.6 here. So in order to do that, you need to have your expression already in this factorization form. So it can be that you have it in the polynomial form, you need to convert that. Okay, and then what? Now we need to determine the a and the b, the constant. So if we know that, we can then determine that later using the z-transform table. Okay, now first we go from here to this step. So what happens there? What you see here is the a here is multiplied by the z minus 0.6 and the b here is multiplied by z minus 0.5. So why do we do that? We would like to have from two fractions one fraction. So that means we have now the same denominator for both fractions. So we can add them up. That's actually shown here. So we can now add the first and the second fraction together since they have the same denominator. And that's what we have here. Now we can say that this expression must equal to this expression. Now since the denominator is exactly the same, so we can divide it out. That means 0.4 is equal to a times the z minus 0.6 plus b times z minus 0.5. So this is a pretty simple expression at the moment. So we need to determine, as said, the a and the b. Now we can use the following method. We can say select a value for z such that one of the unknowns is 0, so it's gone. So we can say let's put a 0.5 here. Why? Because then the b is gone, because that will be then 0.5 minus 0.5, so that will be then 0 times b, and this will be just a times minus 0.1. The left side will stay the 0.4 because there is no dependency on z. So we get 0.4 is equal to minus 0.1 times a, so the a will be then 0.4 over minus 0.1 will be a is then minus 4. So we have now one of our unknowns. And in a similar manner, method, we can calculate the b by eliminating a. So we select now the z is 0.6. Again, the left side stays 0.4. This will be then 0 because the 0.6 minus 0.6. Now the b will be then times 0.1 effectively. So the b will be then calculated like so. So 0.4 is equal to 0.1 times b. So b in this case will be plus 4. Okay, now we have the required a and b. What do we do next? Now the next thing is we can now write our expression, which is then shown here in the beginning, which was then decomposed in these two fractions like so. So we can say, hey, a was minus 4 and b was plus 4, so let's put it in here and there. Now we have our expression. Now we need to go again to the original situation, which was our f of z and not f of z divided by z. So we just again multiply the left and the right hand side by z. That's actually shown here. So you put a z here and a z there. That's actually what you need to do. And then we need to look at the table. So this is now the z transform of a function, and this is now the inverse z transform of a function. So you see here the general expression z over z minus a, and a is a constant, and it can be, if you have it in this form, converted to this expression in the time domain, sample time domain. So you see here 8 to the power k, and we have it actually here. So if you look at this minus 4 and you put it in the front, and also this plus 4 you put it in the front, you see here z over z minus 0.5 and z over z minus 0.6. So actually similar to this table. So the time function at the sampling instance can be then calculated using this table by looking at our expression in the z domain. So we have now this, you see here minus 0.4 times 0.5 to the power k, and then plus 4 times 0.4 to the power k again. And this can be then put together because now we have a 4 and a 4 there, so we can say take the 4 out. By the way, this is valid for integer values, for k is 0, 1, 2, 3, etc. So we can also put it like so. So we can put it 4 here and then 0.6 to the power k minus 0.5 to the power k. Again, valid for these integer values of k. Now the ideal sampled time function can be written using this summation, which you see here is the following. You take this time function at the sampling instance and you multiply that by this delta function at specific situations. So we can then go from k is minus infinity to plus infinity. In this case we start with the 0, so we start here at k is 0 to infinity, and you have all your samples. Okay, let's do that in the next steps. So if you substitute, for example, we can of course do it for infinite number of samples, but let's illustrate it for a couple of samples. In this case we use k 0, 1, 2 and 3, so we have 4 samples, the first 4 samples in this ideal sampled waveform. So we substitute here again the f of kt, which is our function here we just determined, and this delta function is valid for specific situation if the k goes from 0 to 1 and from 1 to 2, etc. So let's work it out in detail. What we see here is now this. You see here the 4 times 0.6 to the power 0 minus 0.5 to the power 0. This part here is the instant at k is 0 for our function we had here. And our delta is the delta function. So Dirac delta is then only valid at t minus 0 times t, which is actually shown here. So we have here the next one, which is for k is 1, which is then 4 times, again, in parentheses, 0.6 to the power 1 minus 0.5 to the power 1, and our delta function, again, t minus 1t. In a similar case, squaring here and to the power 3. And again, the k values here will be changing from 0 to 1 to 3 to 2 and to 3. So we have now 4 samples, 1, 2, 3 and 4 now. Let's work it out because this is 0 in this case, the coefficient here. This will be also in this case 0.4, so we will work it out for these 4 situations. So this is now the worked out version. You see here only delta t, and here delta t minus capital letter T, because this is just 1t, and you have here 2t, and you have here 3t. So this is now the expression. Now you see here this is indeed 0, the coefficient in front of this one, the first sample. The second sample we have here 0.4, because it's 4 times 0.1. The next one is here calculated as 0.44 and then 0.364. Okay. Now this is now our result. Let's also check that in MATLAB. So in MATLAB you can use the command which defines a symbolic scalar value, in this case z. Of course you can also put it as p, but we are working with the z transform, so why not use just the z. This is the expression of our function given here. So we have it here. And then this operator will calculate our inverse z transform of our function. So we do small letter f for the time sampled version, e z trans, and then in the parentheses the z we have here. Now the result is shown here. What you see is that we have 4 times 3 over 5 to the power n. In this case the n is the k what we have here, and minus 4 times 1 over 2 to the power n. Now let's see if this is indeed correct, because this was our result. And you see here minus 4 times 0.5 to the power k, which is actually our second term. And here plus 4 times 0.6 to the power k, which is actually our first term here in the MATLAB result. So indeed the result is correct. So we have verified our calculation and also in MATLAB. So this is exactly as this one. Alright, this was our first example considering the inverse z transfer of a function. We have calculated the time function at the sampling instance and also how we can calculate several samples for this ideal sampled waveform, and also check that using MATLAB command window. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. In the next video we will discuss another example of an inverse z transform. So stay tuned and see you next time in another video.